All right, well, I would like to welcome back to the stage Dr. Elizabeth Heilman. She'll be talking about mastering the water cycle principles using regenerative agricultural practices to enhance soil moisture and improve local weather and patterns in the fight against drought. So please help me welcome Elizabeth back to the stage. So if you're going to mostly stay here, I'll turn this one off because they're both together.
Okay.
That's when bad things happen. Yeah. So, yeah, it'll be on. And he'll pull up the presentation.
I need the clicker. Lauren? Yep. I need that clicker.
It's,
Oh, there it is, right on top. Yay. There we go. So everybody might be getting a little bit sleepy. I'm going to talk about how you can change your microclimate. So Alejandro mentioned that they get about 10% more rain in a super arid environment, and we can certainly change every microclimate and get a lot more rain than we get. The reason that I became interested in rain, in my 20s, I worked in the middle of the Eurasian landmass. I was in the province of China above Tibet that borders on Pakistan and Afghanistan. It's called Xinjiang. And there's Kyrgyz and Uyghurs and Kazakhs and Tajiks, right? So plains, the Central Asian plains people are all there. And my students had to spend a weekend, a month, doing what they called replanting rain. And that was, in the herding people's language, that's what they would call the work of desert reclamation. So in Chinese, it's desert reclamation, but the local lingo for it was replanting the rain. And sure enough, they were able to reclaim desert, replant rain, completely change microclimate. So that was an early important experience for me in terms of knowing that this can happen. So this is the first principle, right? 40% of weather is related to local variables. So what does local mean? Local can be from between 5 and 50 miles. Now, when I say that, you probably don't believe me, right? So I showed this picture. This is the Loess Plateau in China. And this is a before-after the reclamation project. So this shows you how land use, right, affects how vegetation affects what it looks like. And if you imagine being here in the rocky one compared to being over there, can you just feel like the one is more moist, right? And one is going to be cooler, right? So plants, weather, and climate are intimately linked, profoundly linked. One of the issues is that the people that studied rain first and weather tended to be physicists. Rain has an enormous biology to it. And it's a big issue right now because it's a new field called hydroecology or ecohydrology. It's so new they haven't agreed which term, right? And they tend to be interdisciplinary, and chemists seem to be leading it because chemists have had biology, right? And so that's an issue, is that there's profound biological aspects to rain. And so it's taken people across disciplines to go back and learn the biology. You don't have to study ecosystems if you're a rain scientist, and that's an issue. Okay, so here again, do you see that this is exactly the same place? This is a before and an after. So this is a dry ecosystem, and they are getting about 12.4% more precipitation, and the temperature has gone down about 10 degrees in that area. So a lot of the reclamation projects happen in arid areas, right? So we're looking at, you can expect between 10% to about 30% more precipitation when you decide to change your microclimate. The high end of it, where you're getting 30% more, those studies tend to be done in places like the Amazon, where there has been deforestation, and then they reforest it. As soon as they cut down the vegetation, the rain goes down. So if you don't think that there's drought in the Amazon, there are in some places where they're cutting it down. So it goes both ways. You can bring it back, or you can wreck it. Okay, so here's, and then of course you can imagine farmers' income doubled. So this is an interesting study that came out pretty recently, that regional vegetation affects climatic conditions up to 30%, right? So this comes from NASA data where they're just looking at climate, and the number one predictor is just sheerly vegetation. It's also related to soil health. So there's Alejandro's picture there, right? He said that he and his neighbors made more rain. So what are the other factors that influence weather? It matters where you are for longitude and latitude. It matters if you have bodies of water nearby. It matters if you're flat, right? The wind is going sweeping down the plains compared to more topography. Those affect rain. But as little as 5 square miles can form a microclimate. And we actually buy our composting worms from a fellow in Kansas that has a facility that's 5 acres under a roof where he has these piles of, composting worms. And it used to be an airline, manufacturing facility. It rains inside of that 5-acre facility because he has biology working, so it rains inside. So that's the smallest one I know is 5 acres inside. All right, so this is what we're going to talk about. What are the ways that we can get more water and how we can change our microclimate? So the first is we're going to make more rain come down. And I'm going to talk about biogenic aerosols. If you don't know that, that's really common if you don't know that term, because this, again, has to do with the segregation of science, right? So a lot of people that work in agriculture don't study rain. And a lot of the interesting and wonderful insights don't make it back to agronomy. How do you make more water go in? How do you make it stay in and stop evaporation? And then how do we get rain to go back up steadily? And so the soil principles are things that I will mention throughout. So you'll hear these same sort of soil health principles, but through the lens of rain and changing your microclimate. I work in Kansas. We also tend to work a lot in Oklahoma, Texas, eastern Colorado, Nebraska. It's pretty dry in a lot of places that we work. Another story about sitting next to a farmer. So I was at the Green Cover Winter Soil Conference, and there were great presentations for 2 days. And the fellow sitting next to me said, well, I really wanted to learn something about ending drought and rain. And I felt like, didn't we just do that for 2 days, right? But it wasn't explicit, right? It's implicit. So for those of you that are trying to get somebody to change their practice, if you tell someone they can change their climate and get more rain, then that might be more exciting to them than changing their soil, right? So we see pray for rain signs and we don't see pray for soil health. All right, so first, how do we make more rain come? So we're going to talk about cloud seeds, and we're going to talk about biogenic aerosols. All right, so let's talk about how rain starts. You have to have a condensation nuclei. So you have to have a particle that's up in the air, and then the rain molecules come and they attach to it. And then when it gets heavy enough, it falls. Okay? That's step one, is you make a raindrop. Now, what's really important to understand is that there's 2 very different categories of things that are up in the air that sometimes make raindrops. In nature, without human interference, it's overwhelmingly what we call biogenic aerosols, which is things that come from nature. The other things are dust and pollution that are from man-made activity. The biggest difference between these two, the things that are biogenic are much bigger, okay? They're really big. The dust particles can be teeny tiny. The water molecules go onto it and they can't get enough of them to get heavy enough to fall, right? So that's what you get when you have all that tillage dust blowing or a forest fire, right? Those are those tiny little particles. So they're very inefficient. They're also hydrophobic. So tillage dust is part mineral. It has some organic matter on it, right, that dust. But mostly it's not something that attracts a water molecule. Whereas the biogenic ones, and I'll tell you in a minute what they are, They're much, much bigger, and they attract it, right? They're hydrophilic, not hydrophobic. I'm going to mix that up. Anyway, did I mix it up? Okay. Phobic is bad, philic is good. Yeah, so the natural ones attract, the mineral pieces and the dust repel it, and it's hard for the water to attach. Okay. So what are the biogenic aerosols? The 4 big ones are fungi, fungal spores, pollen, volatile organic compounds, and then bacteria that grow on leaf surfaces. And there's more, viruses, just even animal fur, things like that, but those are the big ones. Okay, let's talk about fungal spores. So we all know that if we leave food out, that fungus grows on its own, right? It seems like it comes magically. It does. There's always all sorts of fungal spores in the air. In nature, what happens when the leaves fall down? Does somebody rake it up, or it immediately starts to decompose. So think about picking up a big bunch of leaves and you smell it. Part of what you're smelling are fungal spores, right? So on crops, when you leave a lot of crop litter, one of the things that you're doing is you're creating habitat for fungal spores that are going to make rain seeds, okay? So that stops evaporation. That's good, but you're also growing rain seeds. And biogenic rain seeds make warm, slow, steady rain. It happens in the lower level of the atmosphere. So it's the kind of rain that farmers want. So that means we need to have a lot of different kinds of moist environments. It also means that trees, right, whenever we have a row of trees that are going to help block the wind, it also creates shade, and the shade can be another source of habitat for mushrooms. Okay, the next one is pollens. Okay, so pollens have their purpose for reproduction of plants. Whoops, let me go back here. But pollens also float up into the atmosphere, easily attract rain, and become a raindrop. Now, what you want to have on your farm or ranch are a lot of different things pollinating at different times. Do we want it to rain once? No. We want it to keep raining, right? So in Kansas, we know that right after the corn pollinates, everybody knows next week it's going to rain. And it does, because there's all that pollen up in the air. But if your farm is only contributing one kind of pollen, then you're dry and you're dry and you're dry, right? There's nothing for the raindrops to form around to make a raindrop. So that's a reason for crop diversity, right? There's other reasons to have biodiversity in pastures. But the more different things that we're planting that pollinate, the more your local climate, your microclimate, is giving up these sources of biogenic aerosols. This also means I would like to see every schoolyard have a big patch planted to native prairie with a lot of forbs and flowers. And you can do crisscross paths where the kids can run through. On schools that have these, the kids are out there, they love it, they hide in the middle of it, they play on it, right? So there can be all kinds of public spaces that are also planted to things that are going to pollinate at different times. So a lot of farmers have pollinator strips that are explicitly to help with pollination, but think about biodiversity on your farm, in your backyard, in ditches, any place that you can plant stuff, because you're also growing cloud seeds to help make rain. So this is another one, volatile organic carbons. Anything in nature that has a strong smell is a volatile organic compound. So when you smell a flower and it's pungent, that is a volatile organic compound. Or a lemon. Can we all think of that smell right now? Right, that pungent smell of a citrus is a volatile organic compound. This switched without my permission. Go back. Whoops.
The first principle is that...
Oh, shoot, that's got me talking. Go back. Okay, there we go. All right, and so, but a huge one is evergreens. So that piney smell, that sort of minty piney smell, is another source of a biogenic aerosol. It goes up into the sky, it attracts rain easily, and it helps make rain. So we know that in Canada, where you're in the boreal forest and it's mostly fir trees, it still rains, it still snows. That's because these are here, busy making biogenic aerosols. Over the ocean, whale poop is a good source. You know, there's a whole bunch of things that happen in the natural ecosystems of the oceans that create volatile organic compounds or different forms of biogenic aerosols to make rain over the ocean. How many people knew about biogenic aerosols already? Okay, good. All right, so this is Pseudomonas syringae. This is the bacteria from leaves that is used in snowmakers, right? So there are 10,000 different leaf bacteria that are
The first principle is that 40%.
Got me on it. Make her be quiet. Okay. All right, so leaf bacteria is important. There's at least 10,000 different types of leaf bacteria that serve as these condensation nuclei for rain. So if you think about it, part of what's fascinating about this is that it's the leaf, the plant gets dry, it gets a little vulnerable, it gets a bacteria, it shakes the bacteria off, right? The bacteria goes way up into the atmosphere. These bacteria have evolved so that they have cold shock proteins, so they can stay alive and nice for attracting water molecules when it's really cold in the atmosphere. And so then they attract the water molecule and they fall back down. So that is a coevolution of the bacteria, the plant, and the rain system that helps make rain. Okay, so this is the opposite issue here. We have the dust cycle. So there we have this. And then we have the dust cycle. So what happens with dust? So has everybody seen a bunch of like tillage dust in the sky before? You know what I mean? That kind of dust. And then I live in Kansas, but I've seen California wildfire smoke over us. Have you all seen that where you live? So the smaller particles go up into the upper atmosphere and they travel further away. The heavier particles of the biogenic aerosols, at least half of them stay local, which is 5 to 20 miles. They don't go that far, so they stay more available to the local community. But the dust can carry really far away. It can go hundreds of miles very quickly. What happens is that when you have a lot of these dust particles up in the atmosphere, they do a couple things. One is, I'm a water molecule trying to find a nice, juicy, biogenic aerosol, right? And what am I knocking into, right? There's all this dust getting in my way. Do you understand? So it inhibits the ability of a biogenic aerosol to make rain because it's just full of these little particles, right? And then the little particles, it'll attract, and then they'll evaporate really quickly because there just aren't enough of them. So what they tend to do is they tend to create haze, right? It'll just sit there, or you'll see these clouds and you'll wonder, like in the Dust Bowl, it's like I see the clouds but it won't rain, right? That's what it was, is that it's just, they can't, the water molecules are up there, but they don't have something to latch onto to fall down with, right? So they create haze, and then they create dumping rain, right? No rain, no rain, no rain, no rain. Finally, a little dust particle is able to attract enough of these water molecules that it's heavy enough and it finally rains. So dust particles contribute to much less frequent but dumping rain. Who has experienced that in their state, right? Okay. So that's really important. And what's interesting is the particle size can vary by like 500% between the tiniest and the biggest of these aerosols. Green. So this is just another picture. If you look at that, the small particle is 1 micron compared to a typical raindrop would be 2 milliliters, right? And it evaporates easily when it's dust. So again, this is a natural rain. And when we get those intense rains, even the healthiest of soils can struggle to absorb all of it. And the plants did not evolve to have these intense rains because in the absence of dust and pollution, we have slow, warm, steady, regular rain. So again, this is that idea of this curvature effect, right? The droplets that are bigger can survive. The smaller droplets start off, and it's just harder because of the curvature for them to keep attracting more water molecules. Okay, so this is data that shows us the changes in heavy rainfall. So as you can see, when we start looking at like 75, and it continues on, it shows you up to 2005, we have many more of these really heavy, raining cats and dogs. The irony is if it was really cats and dogs biogenic aerosols, it wouldn't rain cats and dogs. Cats and dogs would not make it rain cats and dogs. You follow me, don't you? Okay. All right. So all of the deserts that are devoid of life, these are man-made. So there's a difference between an arid environment that sustains an ecosystem and man-made deserts. And agriculture emerges out of Mesopotamia, right, in the Middle East there. And the reason that we have all this desert is that you think, well, how could that have been, right? If you think about Iraq or Saudi Arabia, right, isn't it dry? And where I was, just to the south of us was the Talakamar Desert. It was where the Silk Road was, and you have to think, well, how did they ever walk from Central Asia to Europe because you're going through all this desert? Well, the answer is it didn't used to be desert, right? So it changed into desert mostly between about 6,000 and, and about 1,000 years ago. So the reason that we have the Roman Empire invading Europe is not because they're sassy, well, they could have been, but it's because they degraded their own soil, right? They were using tillage, and they invade Europe so that they can plant wheat and bring it back, right? So when you get tillage-based agriculture, it's always a temporary system, and you have to go on and get more land. You can use it for a certain amount of time, and if you don't change your practice, it will be completely depleted, right? And you have to go look for more areas. So we're at the point now where we have to change practice and change deserts, right, back into lush areas. And when we need to take our soils, which are exhausted, we have to bring them a little bit further along. So who knows what are the quotes that we have 30 more harvests? Is that it that we hear, that if we don't change our practices, right? So we have to stop degrading our soil organic matter and switch it. So this is just to review. So bare soil inhibits biogenic rain seeds because you don't have enough diversity of stuff growing. It blows away as dust. That's really bad for a nice rain. Tillage doesn't have crop litter for fungi, right? So that's bad. Monocrops are not providing diverse pollens. Pastures with low plant diversity don't provide diverse grass and forb pollens. Overgrazed pastures, we all know what those look like with those bare spots, right? They also are not providing habitat for fungi. When wood and transitional zones are cut, right, nothing is growing, so those are no biogenic aerosols. There's no shady areas. You're also reducing, you're increasing the wind, right, because it can be a wind barrier. Has anybody ever seen a farmer cutting that last little bit down? I've seen it. They think they're going to get that last little bit of acreage by cutting down all the trees. Go back. Okay, so lots of times parks, schoolyards, suburban yards are biologically bleak. So if you have a yard in this area, it's a good idea to put buffalo grass in. You never have to water it or fertilize it. It's expensive to start with. But then you can plant part of your yard of diverse species, right, instead of planting fescue. It uses water, and it doesn't really do much for your biogenic aerosols. All right, so then those are similar to the soil health principles, right? But it's put through the lens of water. All right, let's talk about getting more water to go in. So a lot of people have talked about this today. We need to stop tillage. We need life above ground. And we have to keep life below ground, right? Live roots, rhizosphere. A teaspoon of soil has between 500,000 and 1 billion different organisms. When I teach about plants, I teach that soil is its digestive system, right? That a plant by itself doesn't really live. Now, when I eat food, does my body digest it? or does bacteria? Right. So that's the same for us, right? We have this gut biome that digests the food, and that's true for plants. Plants cannot get the nutrients that it needs unless it has its soil gut biome working, right? So I teach it as kind of a commensalism that's its stomach. I don't teach parts of the plants and have it end with the roots. And also that the mycorrhizal fungi are part of its circulation and nervous system, right? And that's true because it vastly expands the amount of water that a plant can get, right? Just like our circulation system does. And it's also like a nervous system and a communication system because in a forest or in a pasture, when something happens on the edge, the plants send messages down the mycorrhizal fungi system to the other plants. So if there's a forest fire, the trees send messages and the other plants start putting up fire retardant. The trees do, right? And if there's a beetle or a bug, a pest going on the edge of it, they send the messages through the mycorrhizal fungi and they start making their own insecticide, right? So that is part of its neurology, its circulation, right? We can't have that. And just because I want to criticize higher ed one more time. So when I taught at Michigan State University, I was teaching an ecology class, and you can see what students are majoring in. And I had a student who was majoring in plant biology, and I thought, oh, good, she'll be able to help teach about soil health. And still true, they don't have to take a soil health class to major in plant biology, right? Because the whole program is set up to learn how to use plants for industrial applications, right? All right, that's enough. I won't do it again. Or maybe I will. Okay. So we have to have all this going on so that water can go in. So this is a picture of a tilled field and a no-till field right across the edge. Has everybody seen this in your own lives? So Oklahoma did a study statewide to see how much rain was in runoff, how much was evaporating, and how much was used by the crop. So can everybody think of the answers in your head? What % do you think the crop was using? So, what? 9? That's very bleak. Pessimist. Yeah. 50, right? So it's that same idea. It's not just pray for rain, but use the rain you get. So here's the answers. So only 18%, I think that's still pretty grim, right? So 23% statewide was running off, and 59% is evaporation. And, there's still 30% no-till. So this is statewide. So if it was all conventional ag, it would be lower than that. And again, this is something you've probably seen too, the effect of tillage on infiltration. What % of groundwater, right, do we see in moldboard plowing compared to no-till? That's a huge difference. That's 4 times difference. Okay, so then this matters, right? The type, amount, and function of bacteria, fungi, minerals, and humus affect the pore space. So we have to have space in our soil for the water to go in, right? So everybody's picked up dust and it looks like powder and the water can't get through it, right? So root exudates will glue together the soil. And then bacteria have the capacity to wrap covers around water. They can put a biofilm around it to save it for later. If I'm a bacteria, I am super invested in feeding that plant water. Because if that plant dies, then I die, right? So they have this huge system set up to ensure not just their own life, but to be a backup source for the life of a plant. So to me, a plant is not a plant without its stomach, without its water circulation system, right? Without its neurology. And I think about conventional ag like you take a patient and you cut its stomach out, and then you have to put it on a feeding tube. That's how I think of conventional ag, right? If it's been tilled, you have cut out its stomach and you have to feed it. You have to fertilize it artificially. And you've heard its circulation system. It's kind of violent, but I drive certain directions past a lot of tillage and I have feelings about it. So we want to see all that aggregation so that the water can go in, right? We have to have that pore space. Now this is our farm, so people will say that you can increase soil organic matter quickly. In fact, last month I was talking to like nature center worker kind of conservationists, and one said, well, doesn't it take 1,000 years to make 1% of soil organic matter? Now, some of you that are older might have learned stuff like that, back in the dawn of time about soil, but it isn't true. We can pretty quickly increase soil organic matter. So it's absolutely the case that we have way too much water in the atmosphere and not enough down in the soil. All right, so this was the top 6 inches in the beginning. This is 15 years later. So it went from, we don't have the percent, but it was bleak soil organic matter, less than 2%. And then 15 years later, 8.7%, right? So that's row crops with animals integrated over 15 years. And all we need to reverse global warming is 1% increase of soil organic matter on ag land. And across the world, about half of the land that humans live near is in agricultural use, right? And that's exactly the figure 2 for the United States. So we have to have live roots, the rhizosphere, and increase our soil organic matter. Now, mycorrhizal fungi does a lot, right? But do you see this field? Can you see the different colors? Okay, so the one on the left has mycorrhizal fungi treatment. You can have your seeds inoculated with it, and they should always be inoculated, in my opinion, right? And there's about 30% more water used by plants when you have inoculated it. So there's probably some population on the other side, right? But these are just where they were inoculated, planting seeds. All right, so what do we do to have water stay in? So evaporation is a function of soil temperature and wind speed, right? So do you see the difference in evaporation here? Has everybody seen this over tilled field? You can see it evaporating right there. And this is something that is very dramatic, right? This is the air temperature on a field day. It's 97 degrees, bare soil, 117. Now think about what that does to global warming, just this, right? So we're talking about how land use is a big part of global warming. How much of this doesn't this alone make a difference, right? This is hot. This is ridiculously hot. And then this is a no-till cover crop ground, right? And what does that say? 80.6, right? So that alone is dramatic, and we know that this has a lot to do with evaporation. So this is tilled soil, and then right across the street, same soil, you can squeeze it on the same day. You want to get the farmer and squeeze them, but you don't because you understand they have safety trauma. Okay, so with 5 more inches, right, that's a lot of water. So this is with no crop litter, and then again, right across the street. So you can see what a huge difference it makes to have that crop litter. So that crop litter is a 2-for-1 because you're getting less evaporation and you're creating an ecosystem to grow fungal spores, which are raindrop makers. Okay, so this is also part of keeping more of it. So this is a berm. Has anybody ever heard about the Clark Ranch in Arizona? Okay, so that's a ranch where they just slowed down the water going through pasture creeks and streams by building these rock barriers. So it's not so big that the water can't go over it or fish can't go over it, but it slows the water down. And when you slow your water down, it has more chance to be absorbed sideways, right, into the soil in the bed, and more chance to be absorbed down. So you want to have more water for longer in these little pasture creeks and streams. Now, where we have our ranch in southeast Kansas, we get what would be called a lot of rain, 42 inches. But just like everybody else, we don't have enough. We get these intermittent rains, right, where it's heavy and dumping, and we get drought sometimes too. So our pasture creek completely dried up 2 years ago. So we are going through and we are building these because that will help. It's native grass, it's a rocky kind of a place. It'll help it stay healthy. So I think that tax relief should include building berms. And then the Clark Ranch story, there's a lot, you can, if you Google it, you'll see a lot of different stories about it, but they had different people come and help. So you can invite future farmers, 4-H, Boy Scouts, Girl Scouts, you can hold a party, and give people free beer if they help spend the day building these. They're fun to build. If it's in a pasture creek, it doesn't take that much time. And then you can slow the water down, and it makes a big difference. So, nature, we have beaver dams, right? We have a whole lot of different natural forces that we don't have anymore that used to slow our water down. Now, this is in the Middle East. And what they did was, in the super dry area, they put in these different rock berms to slow water down. And look at that, 8 years later, right? So that's part of keeping the water in the water cycle. Okay, so transpiration. So we also want more plants, whatever plants we want, because we want them to contribute biogenic aerosols, but we also need them to be transpiring, right? So this is a big deal, right? That 40% of weather is based on these local differences. So this is another reason for those of you that are producers to talk with sympathy to your neighbors who might not be doing regenerative farming and ranching, because you need to have, depending on your topography, between 5 square miles and 20 square miles to change the rain, right? So for us, there's some producers that we work with, and they watch the rain come through, and like, the wind's taking my biogenic aerosols over to Martin's farm, in Martin Tills, and that's fair, right? So you really have to educate your smaller community about this, right? So everybody can join hands and change practice so you can change your microclimate. Now, in China, on the Loess Plateau, that was a heavy-duty federal mandate, because it's a communist country and they can give you no choice. That's coming for us in the next 7 weeks, or 8 weeks, or no, it's probably going on now. No, I'm kidding. I'm not really kidding. Only a little bit. Yeah. But anyway, you have to have an authoritarian system, right, to do that, most of which is bad, almost all of which is bad. It's better that we understand the processes ourselves, right, and that we support each other. So this is a reason to bring farmers together and talk about water, right, talk about changing our microclimate, because you've seen those pictures in the desert that Alejandro and his neighbors have 10% more rain. It makes a huge difference. Their ranches are very big. They only need a few ranches to change the microclimate, right? Where my ranch is by myself, it's not enough. If we can get my 2 brothers-in-law involved, a certain number, we can do it. Now, in Clay County, Oklahoma, it's central Oklahoma in the very north. They have a lot of regenerative ag, and it just has to do with individual producers. Like, who was there that decided to make changes, right? So they had a handful of people that were leaders. So Tom Cannon is one, for anybody that ever has been to Oklahoma. 25 years ago, he started to make changes, and they had a lot of good field days, and probably 75% of that county, and it's a tough county, they have a lot of cotton farms, right? About 75% of them are regenerative ranching and farming. And what's fascinating is you can look at the data from 2000 until now and look at their rainfall, and it's about 13% higher than the previous 25 years. And you can look it up. You can see county by county rain. In Kansas, no-till on the plains starts out around Salina. So just because the conference was there, right, they just tended to have more people. It was easy to go to the field days. They have more rain than similar biospheres. They have more adoption of regenerative practices. So the big studies that we've seen are usually heavily devastated places in the Middle East, in China, in Australia, and we can see that the rain comes back, right? We don't have as much good data on making the rain come back and changing your local biosphere in the US because it's so much more patchwork, right? But we can tell if you look at the data, right? You can just see it where we know that we have a lot more regenerative practice. And the reasons are usually social, right? It's where was this conference held? You know, or green cover seed in Blade, Nebraska. That's just where they lived, right? So there's a ton of regenerative farms around there, and they get more rain since green cover was there compared to the previous, 2 decades. So we know it more from bad stories, and it goes both ways, is that we can take a system that has rain and is healthy, and we can devastate it, right? So even in the Amazon now, you think of the Amazon forest, don't you tend to think of it as just a naturally wet place, right? They have cut down trees, they've grazed it, and then they plant soybeans, things like that, and they've started to have drought on these edges of the Amazon rainforest because they're breaking the water cycle so badly. So again, when I was just a young person in my 20s, as a development advisor, they got me because I would go to Central Asia. It wasn't that I knew that much. A lot of people don't want to go out in the middle of nowhere to work for 2 years, but I saw it myself to watch them create oasis towns and bring back the vegetation and bring back plants. It's very possible to do it. But we have to work together, and we have to share this understanding of all these things that will change our microclimates, right? We have to do it. We have to have at least 5 square miles. It seems like about 75% that's healthy within a 5 square mile is your minimum to change your microclimate. More if it's windy. So again, the principle is to work with nature, not against nature. These are all natural systems that we're improving. And remember that prairie plants evolved being intensively grazed. So the bison stand together to graze, and they move just like you do with intensive rotational grazing, because they were afraid that a wolf or a mountain lion would get them, right? So they don't spread out. So that means those plants and that soil bacteria has evolved to be intensively grazed, right? Because this idea of the way that we conventionally graze, it's only about 150 years that we've been doing it that way. So, cattle are not apex predators, right? So the ecosystems are meant to have an apex predator that herd the herbivores close to each other and make them nervous and make them eat everything and then walk here to the next day, right? Now here's another thing that's part of that is that dung beetles are suffering, okay? Dung beetles are my favorite insect. They're the strongest animal creature. They are, the strongest insect in the world. Now, Alejandro, did you have the slide of? You did, that shows what the dung beetles do, right? So the manure should be gone in an hour, all right? 1 hour, it should be gone. So we know that puts a lot of soil organic matter back in. There's methanogenetic bacteria that are in soil, so that helps reduce any issues with methane. But look at the water difference. Look at that. When you have a healthy dung beetle population, you get 130% more water infiltration, 30% more forage, 35% more transpiration just from dung beetles. So you have to bring the dung beetles back. I'm almost done. Okay? So if you are on a place, where people are starting to do regenerative ranching, dung beetles are specific to within like about 100-mile north-south. Go get some dung beetles from somebody else's place and move them. You have to get at least 500 and home them, reestablish them. There's a dung beetle Facebook page where you can secretly trade dung beetles. There is, yeah, it's membership only. You can buy them from Florida, but I worry about that because they're very regionally specific. So it's better to, kind of repopulate them. So if people stop using ivermectin, right, and they stop killing them, you have to reestablish them. That's what you have to do. You have to reestablish your dung beetle population. Now, they can fly 30 miles in a day, but they don't want to. They evolved to go right behind the cattle, okay? Seriously. They evolved to go right behind the buffalo. The buffalo poop and eat, and then the dung beetles come in and they take, right behind them. So if you're conventionally grazing, you're making your dung beetles fly too far. You cannot have a healthy dung beetle population with conventional grazing. And any rancher, if I told you I have a secret way that's really cheap and easy where you can get 30% more forage, wouldn't they be excited? But they always want it to be like a new breed or an injection or, it's like the answer is dung beetles. But this is also really, really important for the water cycle is the insects. So if we don't, this is what we get. You know, we have pray for rain. So pray for your neighbors to understand the water cycle instead. That's our website at Regenerative Wisdom. If you didn't already know, I'm married to Dale Strickler. That's one of his books, is The Drought Resilient Farm. Yeah, and we have yet to see a farm that has a healthy dung beetle population. So go out and reestablish your rain, change your microclimate, plant biogenic aerosols. Are you excited? I know it's the afternoon. I'm just trying to, yeah, we will. Rehome your dung beetles.
Okay.
Yeah, it's really exciting when you see it change. You know, it really is fun. You could stay up there.
Okay, Elizabeth, a couple more questions for you.
Okay. Good range of percent of water use by crops be? Well, crops have an enormously different amount of water use needs by the type of crop and by where they are in the growing season.
We never had it.
So what would a good range of percent water use by crops be? You mean like that Oklahoma? I'd like to see it to be 60%, right? And it depends. The point is that we used to have these warm, slow, steady rains that were like a drizzle, right? And so that's, in some ways, it's a trick question because it depends on the kind of rain. If it's a drizzly rain where it's just rain, you know the kind I mean, right? Where it's misty and just a little bit of rain, and it rains like that frequently, crops can make use of most of that water. The heavier the rain is, the harder it is for an ecosystem to make use of it. And these intense rains that we have are man-made, right? They're not natural. That's not how rain happens in nature, except for fires.
Okay, next question. So how does chemical cloud seeding affect rain quality and soil health?
Terribly. It's a disaster, okay? Now, there's some people that promote cloud seeding, and these guys do not understand biology. They don't. You know, I've had some of them as colleagues. They're seriously convinced that cloud seeding is good because they're going to protect. They're creating this layer to reduce sunlight, right? They really don't understand the whole consequences on the ecosystem because they haven't studied it, right? They don't understand what's going on there. We also know that 4 out of 5 research dollars in the United States are either covert, so it means that the results are never funded, right? Because it's under intelligence agency, or it's proprietal. It's for companies and it's never published because it's like, you know, sponsored research for an industry secret. So that means a lot of the research now in weather modification, it's expensive. You have to collect molecules in the sky, right? You know, we don't know what's going on with a lot of that research. So the last big reports on federally sponsored weather modification are about 12, 13 years old. So we know there's all sorts of weather modification going on. Aluminum doesn't belong in any ecosystem. That's something that's used, right? It's really bad for soil. It's bad for us. So generally, it's a misguided approach to cooling the planet, right? It's better to cool the planet with plants and with healthy soil carbon. But some of them honestly think they're doing the right thing because I've talked with them. Okay.
Okay, back to dung beetles here.
Okay.
Does flood irrigation kill dung beetles?
Does flood irrigation kill them? Yes, it does. But they can fly, right? So they're able to fly 30 miles in a day, right? So it depends on the timing. They can fly away and rehome.
Okay, next question. What are your thoughts on spreading compost on pasture in order to jumpstart carbon cycling and water holding capacity?
Well, I think the best ways to spread compost is naturally, right? So I really am in favor of, if you want compost, is to have it be natural manure. And if you're doing, you know, if you're feeding cattle hay, to have it be bale grazing. Now, if you're doing horticulture, that's different, right? Because then you're looking at compost in a smaller arena. It's very hard to spread healthy compost at scale, right? And fresh manure is completely different than dead manure. So fresh manure is what the soil really wants, and a dung beetle will not go after old manure. So thoughts on spreading compost on pasture? So I would not do it on pasture. I would have the cattle do it. You can bale graze and then do the bales in different places. And it's great for pasture. And steal some dung beetles from your neighbor, or just ask to borrow them, or get on the website for dung beetle trade.
Okay. The impacts of microclimates are well studied in the urban interface. Does it rain less in the concrete jungle?
It does. It rains less. It's hotter and it rains less. And you can see them on those big weather maps. You'll often see those big heat circles that are around urban areas. So yeah, for sure. The coolest place is in Arizona, Brad Lancaster. Who in here knows about Brad Lancaster? Okay, so you can help me tell Brad Lancaster's story. So what he's done is they have, where is he? Is he Tucson? Okay, so in Tucson, he started to, so normally we see that the water in urban, including dry urban areas, is meant to make it leave as soon as possible, right? And so he broke up sidewalks so that the water would channel instead to the, like the grassy area in the sidewalk. He did it himself as subterfuge, but then they started making that be part of the city practice, right? And then we have these concrete canals to put, water that's caught in a city into the river as soon as possible. If you make that a natural stream, and again, you slow it down, right? So there's earth in it, it makes an enormous difference. So they found out that they don't need to use any water from the Colorado River. Just rainwater would be enough to sustain the entire city and urban agriculture if they just started to use what they got, right? So we treat water like it's a problem instead of a resource.
Okay, thank you, Dr. Heilman.
Thank you, everybody.